So thank you for coming. It's my pleasure to introduce and welcome Jana Diesner. Jana received her PhD in,
computer science.
That's easy. Okay, I thought it was something more exotic. Computer science, like data, something. Okay. Computer science from Carnegie Mellon. Okay, got that one. I always get Carnegie Mellon and Case Western mixed up. Okay. From Carnegie Mellon, she's been here for over a decade, and we're just now engaging with her. It was interesting. I learned of her research because of LSST. She received a grant from LSST to study us like monkeys. And then when we realized what she did, it was really interesting, and we wanted to invite her to give a talk and to engage in kind of more informal collaborations and find out what she's doing. So I'm really excited for this talk. Thank you for coming. Let's welcome Jana.
Hi, everyone. I'm so sorry your pizza isn't here. I'll try to make this entertaining for you nonetheless, and I hope the pizza arrives. So let me preface this talk by saying I know absolutely nothing about astrophysics, like negative. So when the folks from astrophysics invited me to come over and give a talk to you, I thought I'll talk about something that maybe you all can at least relate to. So in my research, I do a couple of things at a nexus of social science, technology, information, and one of the things I'm interested in is validating social science theories in contemporary settings. Why does that matter? We often use features from these theories to build models and to explain results we get, and if our theories are wrong, then the rest doesn't make sense either. Second, a lot of these classic social science theories that we use, for example, for feature engineering or for explaining stuff, were built 100 to 60 years ago by observing small groups of people over a long period of time. Now we do this differently. Now we typically have massive data from pretty short time periods, and we get different results. And we could get different results because people behave differently, or because our theories were not correct in the wrong place, or many other things. So again, what I'll show you today is we did look into a couple of theories that explain how people connect to each other for research collaborations, how valid they are, and if they aren't, what we can do about that. And there's your pizza. So I just go ahead and help yourself, I guess.
Yeah, how do you want to do it? Just make sure
just go ahead and
take the last piece. Say something for Jana.
Do you want some? What do you want?
Don't worry about it. Whatever. Just take a moment, get your pizza. I'll keep talking. Yeah. Okay. How people connect to each other has a lot of practical implications also for building tools. When we build things like recommender systems or prediction models for social graphs or models for adversarial attacks and large networks, having features that we can trust and rely on is important. So let's get right into this. The first theory I'll talk to you about is called preferential attachment. And preferential attachment basically assumes that folks want to work with famous other people. So when a junior person joins a lab, they would, according to this theory, seek out somebody who is famous with respect to, let's say, science, which we can approximate through grants or an age index or stuff like that. And the nice thing about preferential attachment, even though it's a micro behavior on an individual level, is that it leaves a very significant footprint in a social network. And that footprint is called a power law distribution of node degree, meaning that if people really do suggest or do pick their collaborators by their fame, then in the end we would see a network with hubs of famous people and spokes, everyone who wants to work with them. them. This distribution is formally, so this distribution from which we recognize this is really a skewed distribution of node degree. But skewed distribution isn't a very fancy term that came from an article from 1955 from Herb Simon, where he defined the families of skewed distributions, but it really became famous under the name of power law, because power law sounds so much more intuitive. That was coined by Laszlo Barabashi in the early 2000s by studying in the internet, where they realized that instead of nodes being distributed equally over the internet, there are really like hubs and spokes, and that's the fingerprint of the internet. So we can measure power law, or we can measure preferential attachment on a personal social behavioral level by the footprint it leaves in a large social graph. The same distribution might be known to you depending what discipline you come from. In other words, 80-20 rule is popular, also known as the Pareto law. If you're in linguistics, you will know this as the Zipf's law, or if you're on social science, this is often known as the long tail. But it all says that a few nodes have like 80% of something, whereas the other 20% have 80% of the stuff. So that's kind of the idea there. All right. So let's see if people really behave according to this when they form research collaborations. The way we studied this was basically by taking large bibliometric data of people co-publishing. Now when you do this, you need to pay attention for node disambiguation. And node disambiguation basically means that if you have people who are referred in different ways, that you kind of figure it out. On the lower right-hand side, you see Stephen Downey, who is a professor at the University of Illinois, Urbana-Champaign, and Stephen Downey, who's a professor at the University of Illinois, Urbana-Champaign. They happen to have the same name. They are different people. They work in different fields, but they have the same name. And our task here would be to figure out that they are different people and not represent them as the same node, but as two different nodes that have the same label but are distinct. And if I told you that they luckily happen to have a different initial, then it becomes easier to disambiguate them. So sometimes our task is to make sure that the people who all have the same name, that we pull them apart into different node names. The opposite of that is merging. If a person is referred to by with different spellings, or Dr. Downey versus Stephen Downey, then all these different variations need to be clustered in the same node. How do we do this? It's pretty straightforward. In the dark old past, the two methods that were commonly used were called first initial based and all initial based disambiguation, where you typically took only first name initial and then the full last name, or all initials available and the last name. And doing that is open to a lot of errors, basically, because if people with common names like Mark Smith, there will be many of them, and they will all be clustered together under one node. But these two methods, all initial and first initial based name disambiguation, has been very common. If you look at oldish, sometimes also current data from big publishers like Web of Science, for example, they still do that. And this works if you have a lot of unique Western names. This changes if you have other people in the system where these assumptions don't hold. The other way you can do it by hand too. That's tedious and not scalable. It also doesn't produce 100% accuracy. People have actually done these studies where they gave senior folks their own resume, and for each of the papers asked them, did you publish that paper? Did you publish that paper? Did you publish that paper? And they didn't necessarily remember. So doing this by hand also doesn't give you a 100% accurate gold standard. The way this is typically solved today, though a lot of publications don't do it, but ideally you would do this algorithmically by pulling in a lot of metadata. Terms from the publication, journal published in, keywords, any metadata you can have, and if you do this, you get accuracy close to gold standard accuracy. So what we did is we took very many data sets from different domains in different countries, and we always took the exact same data set and we prepared it in the 3 different ways that I just explained. It's always the same data set. And I'm showing you a few examples in that table. If we do this, it's always the same data set, right? But depending on how we disambiguate people names, sometimes we even get different number of authors, somewhere between, let's say, 160,000 versus 101,000. That's a fundamentally different number of nodes in a network, and completely only dependent on how the names were prepared. Also leads to a different number of co-authors, for example. And then we basically took these data and we simulated a data set for each of these data sets. We simulated a data set where we used the same number of nodes, similar number of edges, and that's the black line here is always a synthetic generated data set with the same number of nodes and similar number of edges as the empirical data set. And we basically plotted the node degree distribution. That's the solid black line. And that solid black line was generated such that the topology of the graph is a power law distribution. So those are power laws. And then we plotted our empirical data against that. The red line is the first initial solution. That's kind of the sloppiest, but also super common. A little better is all initial disambiguation, and then the best we can do is algorithmic. And you can see that as our effort in data cleaning and data provenance improve from the right to the left in this case, the actual empirical line moves further and further away from a power law. What does that mean? That means that people actually do not seek collaborators that are necessarily famous. This whole idea of preferential attachment to other famous people in science is just an artifact of sloppy data disambiguation. That's what's happening. Or I can also show you this on a little more qualitative level. Here we, from one of these publishing data sets, and here we used each of these methods, algorithmic, all initial, first initial, and we got the top 5 nodes in a graph and their name, depending on a couple of different centrality metrics. Degree centrality is the number of nodes that a node is attached to. Closeness centrality is the shortest path from a node to all other nodes in a graph. Between the centrality measures how often a node sits on the shortest path between any other pair of nodes, and eigenvector centrality is a recursive function of degree. And you can see that with the all initial ones, we get a lot of Asian names. That makes sense because there are a lot of them, and they often have similar last names, and first names start with in our case here, X, Y, and J letters. Whereas the people who are actually most central in these graphs, according to these metrics, don't overlap between algorithmic and any of the common methods. So, and that's what accounts for that, right? As you have more and more people entering publishing with names like that, these methods that maybe used, they were never okay, but they kind of worked, and now they just don't work anymore. They don't work anymore at the level where they suggest that the social underlying explanatory mechanism is preferential attachment. It's just not true. Yes?
Can we step back a little bit?
Yeah.
And it seems to me like you're asking a question of, what makes prominent people in science? And it's almost like the hypothesis is popularity, as opposed to resource allocation, where there are people that have large grants and then people glom onto that. So can you say a little bit more about kind of like why that hypothesis was posed in the first place? Or does that question make sense? Like, I would have said just follow the grants, and when there's money, you can attract people to work with you. Whereas this seems to be like a popularity thing. Like, you could be as popular as you want and all these people, but if you can't pay them, they're not going to be there.
So we did that on a completely different project. That's a current grant we have from MacArthur Foundation. They had pumped $500 million over the last 40 years onto the topic of biodiversity and bioconservation, and they wanted to know, and now they changed that funding program into climate change. Okay, fine. And after those 40 years, they wanted to see what happened in the world with our money. And we did all the data sciencey stuff for them, and everyone else actually knew about biodiversity. Again, I know absolutely nothing about biodiversity. And what we saw, and we did this actually there, we looked at the relationship between having funding and publishing less than you think. It's not necessarily the case that if you have a lot of grants, you also publish more. Maybe because you are busy with managing your grants and doing all that work, but there is not necessarily a strong positive correlation between having grants and publishing. That's still in progress though. So that story is a little more complicated than just funding. But I think that's field dependent. I want to do this at some point. I have this personal conspiracy theory that there are fields where resource dependence structures collaborations. If you need access to the big telescope, then you need a grant for that, and then the telescope goes there and you take your snapshot and that's what you do. But you are dependent on that telescope. In computer science, you don't have that. I show up with my little laptop and do a thing, and that's that, and everyone can do that. So I think that depends a little bit on the field.
Okay.
I hope someone at some point will look me into this. Okay, good.
But this right here, everything here is field agnostic, right? This is just research.
Yeah. This is just people, and actually we did it across different countries. We worked, for example, part of this funding came from KISTI, Korean Institute for Science and Technology. They actually have people, they have a whole office who do this by hand, who disambiguate Korean authors for their publications. That's great, because 80% of people in Korea have 4 different last names, Kim, Park, Lee, and one more. So for them, that really matters. In America, your name is probably pretty unique.
There's a few of us.
There's a few of us. See? So, all right, okay. So we had country level data from Korea, but we also did this for medicine, physics, and computer science. And we get the same results, pretty much.
And fundamentally, your question is, how do people organize themselves in science? Right?
I want to know how people pick their collaborators.
Okay.
And it's not fame.
Yeah.
So that's what we have so far, okay? But we'll get to it. I just said all these things. Also, if you do this like initial base disambiguation, overall, the science sector from like the NSF perspective looks awesome. It's very dense, it's very diverse, people have a lot of collaborators, people publish on a lot of different topics, but that can easily, especially for Asian authors, only be an artifact of data preparation, so it's not really helping anyone. So let's look into a different theory. That theory is called triadic closure. And triadic closure theory says if Adam publishes a paper with Ben, and Adam publishes a paper with Catherine, that over time, Ben and Catherine will also start collaborating because they are introduced to each other, because they might see each other in the lab, and so on and so forth. So you go from like an open triad at time 1 between B and C to a closed triad between A, B, and C. That's a temporal effect. And this has been, so this idea, this theory comes from Rappaport from the 1950s, and it's been shown in very many fields to be prevalent and strong. I'm showing you here a couple of fields and countries where this has been measured, and it's a pretty strong effect typically. This seems to be true that open triads in science close. And the way this matters, for example, for link prediction and recommender systems. And the way this was traditionally measured was by a metric from a very famous physicist, Mark Newman, who basically developed a measure that estimates the number of triads that will close. And it just so happens that the way he structures his metric, it would pick up a couple of false positives along the way. And we always knew that. And because we knew that, Tori Opsahl in 2013 did this measurement a little differently. He basically represented people or like co-publishing as a 2-mode graph. And because the way he did that, it corrected for some of these false positives from Mark Newman's metric, but it still didn't really consider temporal aspects in this metric.
So
yes?
The metric in the first thing
yeah.
Space and time? Or like meaning like?
Just space.
Just space. So,
yes.
So Joe and I were once in the same lab together, and therefore but it's like physical space, like they were in the same location.
Oh, no. This isn't space at all. This is publishing. This is if you had a paper with Joe and a paper with Ben, over time, Joe and Ben would also have a publication together. Doesn't matter where they are.
It's publication based.
Yeah, it's all publication based here. We take publication as proxy for collaboration here. Hoping that's true. So we didn't measure anything. We basically just counted in big data. What we did is we had a couple of different, 4 different large overtime data sets where we looked for all the open triads in year X, and then we gave people 10 years to basically close that triad. So we took the data in year 1980, and then we gave people until 1990 to have a paper together, basically, and we looked for, is that true or not? So there's nothing estimated here. This is just looking for empirical evidence in large disambiguated data. And if we do that, so I'm showing you here the results for closure rates over time for 4 different scenarios. There's DBLP, information and computer science, APS, physics, to the lower left is Medline, medicine, and to the right is the whole country of Korea. And if we use the measures by Opsahl and Mark Newman, we actually do get pretty high triadic closure rates. If we just look for actual evidence of triads being closed over up to 10-year window, we do get closure, but at a much lower rate, at about 1 to 7%. So meaning that sometimes does happen, people do form research collaborations because they were introduced to each other through a joint collaborator, but it's not a very strong effect. Okay, bummer. So that basically means that triadic closure also isn't a good model for link prediction and link formation and recommender systems. Okay, so this didn't work, and that's not a theory we can necessarily strongly. It's an okay little effect, but it's not as big deal as people used to think. So the third thing I will look into with you is called structural balance. And structural balance relates to the way in which relationships are formed over time and sustained over time. This is not necessarily bibliometric data. This is all sorts of social relationships. I'll tell more about it when we get to the specific data sets. So when you look at the way in which 3 people or 3 organizations or 3 countries relate to each other, and we know about the valence or the quality of the relationship between them, there are triads that are stable and triads that are not stable. If you, for example, have 3 people who like each other, this can continue into the future, that's okay. If you have 2 people who have a positive relationship with each other and they have a common enemy, 2 colleagues having a boss they don't like and continuing complain to each other about that boss, very stable. This can continue into the future. If you have 2 positive relationships and 1 negative relationship, that's imbalanced. For example, if you have a good relationship with your parents and a good relationship with your spouse, but your parents and your spouse don't get along with each other, that's imbalanced. That will keep causing tension. And most likely something in the quality of these relationships will change. Likewise, if you have 3 countries that are in conflict with each other, that is not stable, that's imbalanced. And what happens in these imbalanced configurations typically is that 1 or 2 or 3 link signs change such that the triad becomes stable. So for example, in the case of the 3 countries being in conflict with each other, if 2 of them form a strategic alliance and switch their relationship from negative to positive, or at least friendly with each other, then that becomes stable. And this is a micro-level process, 3 people, but if you have adjacent triangles, they can all get impacted, and this whole 3 people making 1 change in their configuration can ripple through a whole graph. Okay, so that's the idea of structural balance. And structural balance has also been shown to be true for a long time over many settings, but it's difficult to measure because you need information about the quality of the relationship between people, and that's hard to get. For example, if you ask people about the mutuality of friendship, I say I'm friends with you, do you also say you're friends with me? The reciprocity rate of friendship is about 50%. And that's set but empirical. So we can't rely on that. So asking people about the quality of relationships has a lot to do with personal perspective, and the reciprocity rate is just low. All right, so what do we do if we can't ask people? And honestly, I don't like asking people because it's tedious, you need a high response rate, you have response effects and all that. So what we did is we got large-scale communication data. We had that from 2 companies and their email data. And we had a couple of other data sets where people actually did ask about the quality of relationships. And we used natural language processing to not have to ask people, but to actually infer the quality of communication, and by that approximating the quality of the relationship from long-term communication data. And what we found, so we didn't ask people, right? We just looked at their communication and communication over time, and we said, oh, it's rather negative or it's rather positive. Yes, there's a question. That's a great question. How does this work with privacy? Privacy is complicated, but whenever there is a federal investigation into a publicly listed company in the US, these data are being made available so that all of you taxpayers can see how your taxpayer dollars are spent on investigations, and at that point, we do have access. Yes, but then it's still our responsibility to anonymize data, and I'm happy to talk about that, but I won't now, but it's complicated, but it's doable. Okay, so by basically doing domain-adjusted analysis computationally for the quality of relationship, what we found is that overall, for the companies we looked into, about 88% of the relationships are overall positive and 12% are negative. The structural balance theorists would say that doesn't count. It's 100% positive or else. So structural balance theory says a graph is balanced if and only if all triads are balanced. And if only one of these triads is imbalanced, then the whole thing is unstable because some change could dribble through the network. And that's not what we found. We found that we get over time and over different periods of how well this company was doing, we get a stable rate of like 88% balance and 12% imbalance. There was another caveat here. So overall, we could confirm this, but not under a strict mathematical definition the way it was originally posed. The other problem with balance theory is in these triads, it's only defined for non-directed triads. But a lot of relationships are directed. For example, communication. The way that I talk to Joaquin does not necessarily mean he also talks to me nice, but it's not necessarily the case. And a lot of relationships are inherently directed, especially in science. Co-publishing is not you publish with each other or you don't, but communication is. So another thing we did here is we basically redefined balance theory and the math behind it to also work for directed graphs. And we had to come up with a couple of new metrics to do that. There is something called the frustration index, which you folks might be familiar with. I'm not sure if you look at graphs in that way. So that basically looks at, in a large graph, how many edges do you have to flip in order to make the graph stable, and you look for the minimum number of edges to flip in order to achieve stability, and that's called the frustration index. And we changed that basically such that it also works for directed data. So once we had that, we had access to a lot more data sets because there are data sets about directed data that have information about link quality, but structural balance theory wasn't defined for that. So now we could do that, and once we did that over a whole bunch of empirical data sets that we didn't collect that already existed, but they were directed, we realized again that structural balance is, we got about 77 to 87% of balance in these systems, and then the remainder are imbalanced triads, and that's just the way it seems to be. So this brings me to my LSST grant. Are you guys familiar with LSST? Yeah? Great. They have a fancy fellowship for astrophysicists. Are you familiar with that for PhD students? Yeah, great. Okay. So that gives you access to a 3-year fellowship program at a site of your choice with a team of 5 mentors. And every year there are 5, is that right? I think there are 5 astrophysics fellowships. I think there are 5 every year. Yes, exactly, the postdoc fellowship. And also 2 social science fellowships. And the idea is that we not only observe astrophysics like monkeys, but that we really look into the practices of collaboration, teamwork, engaging with other fields, data practices, computational practices, and so on and so forth, especially in astrophysics. And my research project in here is actually looking into turnover in these triads. So once we know we have about 20%, 15 to 20% imbalance, what I want to know is, are those the same people who for some reason keep stuck in unhappy configurations? Okay, fine. Or do people rotate in and out of these unstable relations in a way that it still sustains this number at a constant level? So I'm interested in turnover that comes from instability. Is that basically a people feature, or is that a network feature? And we are collecting data in this particular group of folks to look into this effect. All right, so that's my next step here. And I'll show you one more project about how measurement quality issues impact what we think we know about science and science of science. So in 2015, a little note came out in Science that said over the last very many years, almost 200 years, men self-cite each other more in their publications, and that effect is increasing over time. And again, this came out in Science. So we looked into that and we were like, all right. So let me ask you a question here. If this was true, if men would self-cite more than women, and this effect is increasing over time, what would be practical implications? What should we recommend to people? Yeah, and that might have more not. Okay, so that's one thing we could recommend. Sure, something else? Yeah, we could recommend the women to self-cite themselves more, or we could recommend the men to cite more women, for example, right? So all of these are legitimate recommendations coming out from that paper in Science. So what we did was, we first did a replication study. The original paper by Molly King and their colleagues had about 1.5 million papers from JSTOR. They had about 8 million citations, 700,000 were self-citations. And they had a pretty, they did simple name matching for disambiguation, and that's always for me like a trigger thing, right? When I see this on the paper, I'm like, I wonder if their results are actually true or not. So they did name matching, and then they built a pretty straightforward, reasonable model. They basically estimate the likelihood of self-citation by looking at what paper is the self-citing paper in, and what journal is the self-cited cited paper. And it's very straightforward, and the author. And then they basically, measure that effect size, and as you saw, it's like strong for men. And we took similar amount of PubMed papers. Why did we use PubMed? Because in 2002, PubMed introduced first names as part of author names, and that helps with disambiguation. But also for PubMed, a lot of funding has gone into building correct author disambiguation models, and that helps us to have better quality control over disambiguation issues. And we used Authority, which is a public tool. It's from the School of Information Science. Here, everyone can use it. And that does name disambiguation based on an algorithmic prediction model. That's highly accurate. And when we use our better data and the exact same statistical model that they had, we get basically the same effect. We see that men self-cite more than women. And we did this for both the first author. And is in your field, is the first author or last author more senior?
We don't do the last thing. The first one is usually
yeah.
usually more junior.
Okay.
But it depends.
So that totally depends on fields. In PubMed, you see a lot of like random or alphabetic. In computer science, typically the most senior person goes last, the workhorse goes first. But social science completely different. The senior people are often in the front, for example. So it's different. And that's why we did look at every position, like first author, the group of middle authors, and the last author. And no matter how we did it, we still found a positive effect, like an original paper, that men self-cite more than women. All right. So you can see here that data quality might impact the effect size a little bit, but we still get the same effect. In the next step, we added additional features to the statistical model. And what we did is we did a simple log likelihood forward search algorithm that at every point in time takes all the data and picks the variable that explains most of the variance in the data in terms of self-citation. And we start with an empty model. And then if we only use gender, that's the gray bar to the left, that's basically the replication study. If we use no feature other than gender, we basically replicate the original paper. I showed you that. But as soon as we let go of forcing gender to go first and let the algorithm decide which feature to pick first, such that it explains most of the variance in terms of self-citation, other features come first. How long has it been between the original paper and the paper that's citing that paper? Age means like how many years have you been in science, academic age. What journal, citation count, reference count, country, novelty score, collaboration science, number of co-authors, and so on and so forth. And if we let the algorithm do it itself, gender is the last feature selected, meaning it explains the least variance in comparison to these other features. And what you also see is like this gender effect kind of goes away and flips a little bit. So if we consider all these additional features, women actually self-cite a tiny little bit more than men. That's a very different story. And that story has nothing to do with changes in science or behavior. It only has to do with data quality and more so statistical modeling decisions. So we looked a little bit more into that, and we wanted to understand, so, okay, women self-cite more. Okay, let's look a little bit more into this. What we saw is that overall in PubMed, it's medicine and biomedicine, but also adjacent fields, more women join the workforce, but also more women than men leave the workforce, and overall women have shorter career spans in that field in general. And the real culprit here is not self-citation, it's really that women have less of a chance to self-cite their work because they stick around in science less long than men do. So they have less of an opportunity to self-cite. What we found overall that self-citation is good. So let me tell you, self-cite away, it's great. Self-citation is the hallmark of successful authors who give their own papers a visibility boost early and often. It's a great thing. But men have more of a chance to do that because they stick around longer. So if we look at these results, yes, there's a question.
Previous work?
Yeah, we looked into that too. So we did this a little bit differently. We looked at what papers don't get self-cited. And that's often from people who switched fields. We call them orphan papers that, got published, but then didn't get cited, especially not self-cited. And that's when people either left and nobody else cared, or when people switched fields. But that doesn't differ for men or women. That's an equal opportunity choice to make. Okay.
So the disparity between self-citation is basically leaky pipeline.
Yes, exactly. It's a leaky pipeline problem, and it's pretty easy to show. Yeah, exactly. The gap in self-citation, leaky pipeline problem. Was there a question in the back?
How accurate is the estimation of gender based on immoral, just based on the name? How can you predict?
No. We don't predict gender just on the name. People used to do that, but there are many more features you want to consider. So we have a likelihood value of gender that, again, depends on a lot of things. And it's also our gender prediction is country and ethnicity specific. We have a tool for that. It's called GNNI, G-N-N-I. That's, again, trained on large statistical, disambiguated, accurate data. And we also have it for ethnicity, if people care about that. We also looked into ethnic differences.
Okay,
Yeah. So because it's oftentimes these three things, right? Gender, ethnicity, and yeah. Also, we didn't throw away data. Oftentimes, when you look into these gender data, they often do have some gender tool, and then they take all the names that are clearly masculine or clearly feminine, and the rest just is not considered for analysis. Okay, so we didn't do that. So the recommendation here would not be to tell women to self-cite more. The recommendation here would really be to encourage organizations to do stuff to keep women in the workforce. They come, they just don't stick around. All right, so this classic case of Simpson's paradox, where once you do more sophisticated statistical modeling, your original effect is kind of explained away or goes away or flips around. And we are currently extending this to see under what conditions does actually diversity in teams with respect to gender, ethnicity, and intersectionality lead to publication effects. That's currently a thing we are working on. So that's all I wanted to show you. Thank you very much to the sponsors, and even more so, thank you very much to my wonderful team. And with that, I'm happy to take any more questions or comments you may have. Thank you.
Any questions for Jana? Yeah, so sorry, regarding the self-citation thing, how many years of data have you considered there?
We had a sliding window, so it's always 5, 5, 5. We have 5 years of entering, 5 years of being, and then give people 5 years to leave, basically. So it's a sliding window of always 5 years.
I'm just wondering if you have taken into account, for example, the minorities may not have a bigger chance of publishing earlier, which is probably growing right now.
Can you say that again?
So all the minorities, they might not have had the opportunity earlier, but maybe it's growing right now. So that can change.
Maybe,
things.
yeah, that would be great. I'm happy to run this again in 10 years.
Yeah.
Yeah.
Any other questions? I have a question. Can you say more about exactly what you're going, like the answers you're hoping to come out of your research analysis? So you have a question, but what is it you're trying to answer?
My hypothesis is that turnover depends on personality, not on structure. But that's just my crazy personal guess.
And personality of the collaboration or the individual?
Individuals. But, you know, X seeks company. Doesn't have to be misery, but apparently it is. I don't know. And I want to see if that's true. If there are certain people who stick around in negative configurations, or if that's not the case, people do leave, but then somehow somebody always gets dragged in.
And how do you measure that?
So a question, right? We need quality of relationships. So we are still debating on how exactly we will get that out of people. Yeah.
And you're going to do this with real people within the LSST ecosystem? Okay.
Yeah, but with them we do a lot of things. So basically the main mechanism, there will be a survey and we will ask questions. And we have two things. We have a survey that they fill out, and there's also follow-up qualitative interviews that my colleagues in the social science team are doing. They look into different things. One of them studies impact of caregiving and parental duties on science. One person is interested in gender and race, so they ask different things. I'm interested in the structural question, yeah.
Any final questions? All right, let's take a speaker again.